There are a lot of different scenarios in which substitution can come about. We're going to look at a few of those scenarios in the next few examples. Because there's so many opportunities for substitution to come into play and how substitution works, it's going to be really difficult to go through the entire list of every example that you could come up with. I'm going to try to give you some representative examples of what could happen. Let's take a look at example 4. We want to use substitution to integrate 12x squared over x to the third plus 16 with respect to x. In order to do substitution, the first thing I want to do is ask myself, what part of this function should I make my u? In this scenario, the best thing to do is let your u be x to the third plus 16. Now, the reason for that is that I have a polynomial here. I know when I take the derivative of x to the third, I'm going to get 3x squared. And notice I have an x squared in the top. So I'm hoping that when I take the derivative of x to the third plus 16, that derivative will match up or in some way with this top. The other way I can think of it is that even though this x to the third plus 16 is in the denominator, I could have rewritten this problem and put the x to the third plus 16 as being multiplied times 12x squared, but having the x to the third plus 16 being raised to the -1 power. Let me show you that. So what I'm saying is that sometimes people will think that they're doing an integration and they'll say, oh, this is like 12x squared times, in parentheses, x to the third plus 16 to the -1 with respect to x. This is akin to those first couple of problems that we did. We had a polynomial raised to a weird power. In this particular scenario, I don't like raising things to -1 power. I like keeping them in the denominator. If this was raised to a -2 power or -3 power, I'd probably rewrite it like this. But since it's a -1 power, I'm going to leave it like that. We're going to let u be the denominator. When I take the derivative of u with respect to x, I get 3x squared. That means I can get a du if I can get a 3x squared times dx together. Well, I can do that here. This is what I was talking about with building that intuition, saying, oh, x squared is the derivative of 3x squared. Did I say 3x squared? Excuse me. 3x squared is the derivative of x to the third. So the intuition would say, if I let my u be the bottom, then maybe I can pull out the derivative piece I need from the top. In this case, I can, in fact, do that. I can take this 12x squared, and 12 is just 4 times 3. And instead of writing it in the numerator, I could have just multiplied 3x squared times dx. In other words, I pulled and factor out a 3x squared from the numerator and just put it next to the dx. If we understand how multiplication of fractions goes, we know that this is a correct thing to do, or a correct thing that we can do. At this point, what we're going to do is we're going to take this expression and do our substitution. The 3x squared dx gets exchanged for a du. The x to the third plus 16 gets exchanged for the letter u. This is why I didn't want to put a -1 as my exponent, because I kind of knew it was going to end up looking like this. Anytime you have divided by u, you want to utilize natural log, again, divided by u to the first. So this would be 4 times the natural log of u plus a constant. Again, I'm putting parentheses around the u. That's what you should do in Moodle as well. But sometimes you'll see people write absolute values around this u. After I've done that, now we can back substitute 4 times the natural log. Remember, u was x to the third plus 16. So 4 times the natural log of x to the third plus 16 plus a constant of c is the antiderivative we're looking for. That's one example that you could come across where we have something in the denominator that we want to make our u, and then we can factor out whatever was in the numerator to place next to our dx in our dx du exchange. Another scenario that you could come across is one which has a polynomial underneath the square root. Now remember, square root just means taking something to the 1/2 power. This is nearly equivalent to those examples we did earlier, like this one, where I had a polynomial to a power and then something out front. Polynomial to a power and then something out front. I have here polynomial. Even though it looks like a square root, I could have replaced that with the power of 1/2 times something out front. This is going to work like those initial examples we did in this section. It is going to be easier to integrate this if, or I should say, it's going to be easier to integrate eventually if I rewrite that square root as being raised to the 1/2 power. So I'm going to do that. My u is going to be the polynomial that's being raised to a power. In this case, that's x squared minus 16. The du with respect to x is going to be 2x. That means du is equal to 2x dx. I can factor an x and bring it back to the dx, but that still doesn't give me a 2. So what I can do, if I want, is to divide both sides of this equation by 2. And that will mean 1/2 du is equal to x times dx. Now I am ready to do my exchanges. The x squared minus 16 is getting replaced with a u. My x times dx, maybe I should have rewritten this first before I did my exchange, but all I'm saying is I can bring the x back there. The x dx can get replaced with a du. And now I'm ready to integrate. If we integrate, remember we raise that power by 1. 1/2 plus 1 is 3/2. And then divide. 1 divided by the fraction 3/2. Well, that actually gives you the fraction 2/3 plus c. In this scenario, u was x squared minus 16. So what we really have here in terms of x is 2/3 times x squared minus 16 raised to the 3/2 power. This is my final answer. Notice that 3/2, a 3/2 power, there's lots of different ways to write that. You could go back to roots and do a square root and then cube the square root. But I think when we have a 3/2 power, it looks a little bit nicer just to leave it as 3/2 power. This is the example of substitution with a square root. I would like you all to push pause on the video and try this problem. 1/4x minus 9 integrated with respect to x. Go ahead and do this one and see how it works out.